In this lesson, we're going to look at finding displacement from a velocity graph, and to do that, we have to remember a few things. First, we know that change in position, or displacement, is equal to velocity times time, but that's only true if the velocity is constant. If we're changing speed, then this falls to pieces. And so we have to use another way of finding displacement from velocity. And what we do is we use an average velocity. So let me show you what I mean. If we come down to this velocity time graph, we have a lot of different velocities that are occurring. Initially, for the first 3 seconds, we have a constant velocity, and we can see that the displacement for the first 3 seconds is equal to the velocity of 2 meters per second times 3 seconds, and that's 6 meters. And that works because the velocity never changed. But for the next second and a half, this doesn't work, because if I wanted to say the change in position is equal to velocity times time, well, I have my time of 1.5 seconds, but I don't have a velocity. If I picked 2 meters per second, my initial velocity, then I would say I've gone 3 meters. But that's not the case, because at the end of this, I'm only moving at 0 meters per second, not 2 meters per second. So I haven't actually gone the full 2 meters that I'm claiming, or 3 meters that I'm claiming. So I can't use the initial velocity. I can't use the final velocity, 0, because then I haven't moved at all. So I can't use either of those. Instead, what I do is I use the average velocity during that interval. So in my first little segment, we went 6 meters, 2 times 3. And I want you to see what that is. That's 2 meters per second, which is this height, that distance here, times this 3 seconds, which is a base, right? So I basically took the base times the height, and I found the area of that rectangle, and that area is 6 meters. So that's how far it moved. Now this next little one, I'm going to use the average velocity. The average of 2 and 0, 2 plus 0 over 2, because there's 2 measurements, is 1 meter per second. And we basically used an average of 1 meter per second for 1.5 seconds. So I'm going to take 1 meter per second times 1.5 seconds, and I get 1.5 meters. But let's look at what I really did. I used an average, which means I used half of this height right here. So I used half of 2 times this distance here, that base, 1.5. Well, half base times height is still an area. So this area is 1.5, and so I get the displacement is 1.5 meters, and I did it the same way. It's still the area under the line and the time axis. So this area was 6, 1, 2, 3, 4, 5, 6 squares. This area, it's a little bit hard to see because I scribbled it all in, but this area is 1.5. I have my one box here, missing that corner, which we make up for here, and then my half here. So its area is 1.5. We have a displacement of 1.5 meters for this next little bit. Those are both positive because my velocities are positive. We can apply the same thing here. So I've got my 6 meters, 1.5 meters. This is also 1.5 meters by the same argument, but it's negative because my velocity is negative. So I have 1/2 times -2 times 1.5, and this is negative 1.5 meters. And then finally, I have this last little bit, -2 times 1 second, which is -2 meters. So we can see for the last few seconds it's got negative displacements, and the areas were below the axis. So I'm saying area, but it's not a surface area, it's how much area was captured by this graph, and that is a displacement. So what I know for sure is in the first 3 seconds this thing went 6 meters. In the next second it went, or second and a half, it went 1.5 meters. Then it came back 1.5 meters, and then it came back 2 meters. And all of those are the areas under the curve for those little intervals. And that means I can figure out that this thing actually has an overall displacement of 4 meters. But you'll notice all of these are displacements. None of them actually tell me where the object is at, because velocity doesn't show position, it tells me speed and direction. So I know it's moving away at a constant speed, I know it's moving away slowing down, I know it's moving towards getting faster, I know it's moving towards at a constant speed, but I actually don't know the exact speed or position. If I do know where it started, then I actually can figure out what the position time graph looks like. And so that's what I'm going to do over here. I'm going to say this thing started at 1 meter in front of the detector. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7. Right, I only need 7 seconds. Here's time. There's position. I'm going to say it started at 1 meter. So my initial position is right here. I know for the first 3 seconds it goes 6 meters at a constant speed. So at 3 seconds I've got to be 6 meters further, which is all the way up to 7. And it's at that constant speed of 2 meters per second. So I should be able to go up 2 over 1, up 2 over 1, up 2 over 1, and end where I want. And I did, right? There's my 6 meters per second. So this is a straight line on this position time graph because the velocity is constant. But for the next second and a half, which is right here at 4.5 seconds, the thing is still moving away, but it's getting slower, which means my line has to curve now and actually end up flat. And it goes 1.5 meters. So in 1.5 seconds, it goes 1.5 meters. So it's got to end right up here. And while it's doing that, it's got to be getting slower. So my graph actually curves there. And then it moves 1.5 meters back the other direction, back towards it, getting faster. So it starts flat and gets steeper here, and that's what this shows. So this curving line right here shows a change in direction and a change in speed, right? It's getting flatter, so it's getting slower. Now it's getting steeper, so it's getting faster, but it's getting back towards. And then for the last second, it's going 2 meters per second. So for the last second, this graph is a straight line. So I actually created a position time graph from this velocity graph. And I'm going to double check, did I end 4 meters from where I started? I did. I started at 1, ended at 5, so my total displacement is 4. So I found the areas under this curve to find my displacements. I remembered that curving lines show that the velocity is changing, and I have to curve them correctly, right? This is getting slower, this is getting faster, and then I can end here. And all my displacements match up, all my velocities match up. In fact, the slope of this line right here is up 1 or up 2 over 1, so it's 2, which is this slope. And for the next second, the slope is still 2, and for the next second, the slope is still 2. So for this whole section of the graph right here, the slope is 2 because the value of the velocity is 2. But then this slope is getting less steep. Right here, that's a horizontal line because the value of the slope right there is 0. Right here, the slope is 1, and so right here, this thing's got a slope of 1. And right here, the slope is 2 because right here, this is 2. Right? And then the slope actually becomes negative, and so this line goes negative. And so at any instant in time, the slope of this line is, the value of this line is the slope of this line. Okay, so if we put this all together, some things to remember: the value of the velocity graph is the instantaneous slope of the position graph. So if I look at the velocity graph and it says it's moving at 2 meters per second, then I know my velocity is 2 meters per second, so my position has a slope of 2. Okay? If that velocity changes, then the slope over here changes. If the velocity is changing, so is the slope of the position time graph. Remember, horizontal lines on a velocity time graph are straight lines on position graphs. This right here was a horizontal line. Let me erase. At the beginning, we have this horizontal line right here. And this line over here is straight. It's not curving. It's going at a constant 2 meters per second. But this line is sloped. That indicates that the velocity is changing. That indicates acceleration. So over here, this line is curved. That's how we show a changing velocity, because it's a changing slope. And then area under a velocity time graph is displacement. That works whether it's rectangle or a triangle, but so that means you have to know that the area of a rectangle is base times height, but the area of a triangle is half base times height, right? Area is half base times height. So you can get your displacement from this. Now remember, displacement is not the same thing as position. So just because you know this does not mean you know where the object is. So I have to tell you where it starts, but once you know that, you can figure out where it ends and where it's going to be.